All right, today we're diving into a paradox from the world of nuclear energy that, honestly, seems to break the rules of common sense.
It sounds like a riddle, right? If you take out the hottest part of something, you'd think the rest would have to get even hotter to pick up the slack. But in nuclear engineering, that's not what happens at all. Let's find out why.
So here they are, our two main players. On the left, you've got your standard, solid uranium fuel pellet. This has been the workhorse of the industry for decades. And on the right, we have the challenger, the annular or hollow pellet. It's basically the same thing, just with the center core out. A really simple difference, but with some profound consequences. Okay, so let's put these two designs head-to-head and really see what makes them tick. Now, the key to this whole analysis, the really important part, is that we're comparing apples to apples here. Both of these pellets have the exact same outer radius, 4.10 millimeters. The only difference is that design B has that 1.20 millimeter hole right in the middle, and that single change is what makes all the difference.
But, this isn't just a simple geometry problem. In the real world of power plants, there are very strict rules that completely change the game.
And this is the most important rule of the whole game. A nuclear power plant is kind of like a car engine that's always running at a specific RPM. It is designed to produce a constant, steady amount of power. So for our comparison to mean anything, both the solid and the hollow fuel rods have to produce the exact same amount of energy, 25 kilowatts for every single meter of fuel. This is what's known as the linear heat generation rate. So here's where it gets really interesting. Because the annular pellet has that hole in it, it physically holds about 8.5% less uranium fuel. But remember the rule from the last slide? It still has to produce the same total amount of power. How on earth is that possible? Well, it has to work harder. The fuel that's left in that hollow pellet has to generate heat 8.5% more intensely just to make up for what's missing. And this is the core of the paradox. We've removed the hottest part, and now the rest of the fuel is having to run even hotter, at least on a per gram basis. So why doesn't the whole thing just, melt? The answer, it turns out, lies in the physics of heat transfer. It's all about how profoundly the shape of an object can dictate how it cools itself down. Okay, so in a normal solid fuel rod, heat is being generated everywhere inside the uranium. Now, the heat that's generated right at the edge can escape pretty easily into the coolant that's flowing by. But what about the heat generated deep in the center? Well, it has to travel all the way through all the other layers of fuel just to get out. It creates a thermal traffic jam, and the temperature profile you get is this classic parabola, with the peak temperature right smack in the center. But now look what happens when we introduce that hole. The math completely changes. That void acts like an insulated boundary. Heat can't flow into the empty space. Suddenly, every single point within the fuel is closer to an exit. It's closer to that outer surface. There's no longer this deep central core where heat can get trapped. So, after all the math and all the physics, what's the final result? When we put these two designs head to head under that strict 25 kilowatt per meter rule, who comes out on top? And here it is. This is the hero graph of this whole analysis. That top curve, that's the solid fuel, peaking at over 1,000 degrees Celsius. The bottom curve is our annular hollow fuel. You can see the advantage immediately. First, we have literally removed the material that would have been the hottest. And second, because the remaining fuel is just a thinner ring, the heat has a much shorter path to escape, which keeps the overall temperature way down. It's a double win. And the final numbers really tell the story. The solid pellet hits a maximum temperature of 1062.5 degrees Celsius. The annular pellet, even though it's generating heat more intensely, tops out at only 910.8 degrees. I mean, that's a reduction of nearly 152 degrees. This isn't just a minor improvement, it's a huge boost to the safety margin. By literally taking material away, we've made the entire system safer. But, as with pretty much any engineering decision, this incredible safety benefit doesn't come for free. There are always real-world trade-offs you have to think about. And this slide really lays out that classic engineering trade-off, safety versus cost. The benefits are undeniable, a massive drop in temperature which leads to less stress on the fuel and a much bigger safety margin against melting. But there's a catch. With less uranium in each rod, you either have to use more expensive, highly enriched uranium, or you have to build more fuel assemblies to get the same amount of energy over the reactor's lifetime. But when your primary concern is safety, the verdict is crystal clear. The source analysis concludes that the annular design is just plain superior.
It's a powerful safety upgrade that could allow future reactors to operate more efficiently or use fuel for longer, all while having a higher standard of safety. And that's exactly why this is a key focus for next-generation nuclear designs.
So the key takeaway here is this. By removing the inefficient, heat-trapping core of the fuel, engineers created a more robust and safer design. It's a really powerful reminder that in complex systems, the solution isn't always about adding more, it's about improving the geometry and efficiency of what you already have. Which leaves us with a final thought. In a world full of complex problems, where else might the real solution be to subtract rather than to add?